Okay, so this is ECE 3030. I think it's a required course for the computer engineering degree. And in this course, we are going to discuss the physical foundations of the computer engineering. And this is for 3 credits. And we are going to meet Monday and Wednesday afternoon. And actually, this is a session A. We have a following session B after this class. So we are going to meet here, 1 year, 340. And the course website is Canvas. So we are going to post all the documents in the Canvas system, like the lecture slides, homework. And also you can send me emails through the Canvas system. And also you can have discussions over there with the TAs. And I'd like to have a very brief introduction about myself. So I'm an associate professor with the ECE here. And my office is in the Pettit building, or this MIRC Microelectronics Research Center building. Office number is 116. So you can go to that building through the bridge on the 4th floor here, through the 1 year building to the Pettit building. So it's just the next building to here. And the office phone number is that one. But the best way to reach me is through the email as listed there. So we are going to have office hour every Friday and 10 to 11. If you have conflict with this time, then we can set up some individual meetings by appointment. And also we will have TA support for this course. But at this moment, I haven't got any confirmation from the department who is going to be the TA. But I think there will be 2 TAs for this course. And the TAA will have office hour as well. We are going to set up that time later as I identify who is going to be the TA. So stay tuned for the TA information. We will update that later. So any questions so far? All right. So myself, I got my PhD degree in electrical engineering from Stanford back in 2013. So right after graduation, I joined the Arizona State University in Tempe, Arizona, from 13 to 18 as assistant professor. And over the summer of 18, I moved to Georgia Tech here, and now I'm the associate professor here with ECE. So my research area is in the field of the VLSI and the nanotechnology. So here I list some of my research interests here, like the nano-electronic devices, non-volatile memories, like the memory used in your SSD, solid-state drive, and the circuit device interaction, and the design automation. And also in particular, I'm very interested in this neuromorphic computing of the deep learning accelerator. So we are building the hardware for the machine learning, basically, using the device technologies. And if you're interested, that is my website for my research lab. This is just for your information. Okay, so the prerequisites for this 3030. I assume that all of you have done the 2000 level 2020, like the fundamentals of digital system design, and also the 2040 circuit analysis. So basically, we are going to use those 2 courses as a prerequisite for this course. From there, you have learned the digital system basics, like the logic, and NAND law logic, and also the Boolean algebra, and the basic organization of the computer system, like the data path, memory, and the instruction set architecture, and so on. So those will be the foundations for this course. And also you have learned the basic circuit theory from 2040, and basic concepts of DC and AC small signal analysis. But for this course, we are going to mostly discuss the digital system. So that means we are going to dealing with the devices to operate in the digital domain, like 0 and 1s. But actually the devices operate with the analog signals. But we interpret that as digital 0 and 1. We are going to have more discussions later. So those are two prerequisites. And then the follow-up courses after the 3030, there are some options for you. So after 3030, I think there will be a 3150, which is a more advanced digital system design. So it's called VLSI and advanced digital design. So that course is going to have more in-depth discussions on the circuit design using transistors for the digital system design. And in this course, we are going to talk about mostly on the single device level, the building block, the transistor, and the most complicated circuit we are going to discuss maybe is an inverter with 2 transistors. And then the following up courses may discuss the circuits with more transistors. So here we are only limited to 2 transistors for the inverter. And then for there is 4130 advanced VLSI. So that is, I think it's a mixed undergrad and graduate level courses for the advanced VLSI. In that courses, I think you are going to learn how to build a real microprocessor using the silicon technology, using the transistors. That means you are going to dealing with thousands or even tens of thousands transistors in the silicon technology. So those are the possible follow-up courses along this path. So any questions here? All right. Okay, so this is maybe what you care about most. So we have assignments like homeworks. So that will consist of 30% of your total grade. And then we have 2 midterm exams, midterm 1 and midterm 2. Each of them is 20% of your total grade. And then the final exam will be 30%. And the final exam will be cumulative. That means it will cover everything. Okay. Maybe midterm 1 will cover the first few lectures, and the midterm 2 will cover materials after midterm 1 and before midterm 2. But the final exam will cover everything. So that's why we have more percentage to the final. And your final grades will be curved using all the components, like the homework and all the exams. And we will look at the distribution, and then we'll decide the letter grade based on that. So any questions?
Has the dates for the midterms been set already?
Not really. So we have a tentative schedule. I will show that later in the slides. But those dates are subject to change. But we have a rough guideline, like maybe late February, late March. Yeah. For late February for the midterm 1, and then late March for the midterm 2. The specific date is to be determined. And the final exam is according to the registrar's schedule. And I couldn't book that. So that is for final.
Do you guarantee that 90 is an A, 80 is a B, that kind of thing?
Not really. So because I will look at the performance of the whole class. For example, maybe this semester, maybe because of the exams are difficult, so none of you get above 90, then of course I cannot, there's no A in the class, that's impossible. So I will look at the distribution, yeah. But yeah, roughly if we make everything according to the distribution, then we will get maybe roughly 30%, maybe 40% A, and maybe 40% B, and the rest like 20% C. This is just a rough estimation at the beginning of the semester. We will decide that later. Any other questions?
Do you post your lecture slides on Canvas, or like these slides, do you post them?
It's already there, I think. So I posted yesterday, so any of you found those slides there? Okay, so it's already there. Yeah. So I'll try to post the slides before the lecture, and also we will have a marked version of the slides after the class. I will upload that because I will hand draw some equation derivation during the class. So I will save that marked version for you after the class. And also we have recorded the lecture through that camera, and I will process the video after class, and then I will upload that to the maybe YouTube, and then later you can review the lectures if needed. All right. So this is assignments and grading, and some policies for this course, and the midterm finals dates as we discussed. Then the homework and assignments are due on the due date, okay? And there's no late submission. We don't accept the late submission. So if you miss the deadline, you will get 0 for that homework. So of course, if you are sick, then you need to let me know in advance. Maybe we can accommodate that. But normally, we will not accept the late submissions. If you need to submit late, you need to let me know in advance, okay? I will not accept any requests after the due date. And questions regarding the grading of your homework or exam need to be asked within 1 week after the homework or exam is returned. So if you have questions on your grading, then please ask me or ask TA. Proper TA will grade your homework. So ask them within 1 week after the grades are posted. So then you will get a prompt feedback for the grading. I don't want to have this kind of situation at the very end of the semester. Then you come to my office and ask me for like 1 more point on your first homework. So that will not be accepted. So if you have questions, ask immediately to the TA or to me. And then I posted the syllabus as well in the Canvas. And there are discussions on the academic integrity and accommodations for disability and so on. So those are the standard items in the syllabus. I will not repeat here. You can refer to the syllabus posted in the Canvas.
Do we drop the lowest homework score since we don't accept late submissions?
Nope. We don't have too many homework, maybe 5 or 6 homework in total, so we will not drop any lowest score.
Are we allowed to use cheat sheets during?
Yes. Yes, you will allow cheat sheet in the midterm and final exams. Yeah, you will allow like 1 page, maybe for the midterm and 2 page for the final. So any questions? All right. Okay, textbook. So there's no official textbook for this course, and within our faculty we are discussing internally to change to a new textbook, probably for the future semesters. But at this moment, we don't require official textbook but we do have some recommendations for the supplementary reading. And the first one is from Professor Chen-Min Hu of UC Berkeley. And he had this modern semiconductor devices for integrated circuits. And actually, you don't need to purchase this book because Professor Hu is very keen to share the book freely online. And you can download the textbook from that link. And we will use some of the chapters from that book for our discussions. So this book is mostly for the basic semiconductor physics and devices. And we have a second reading in supplementary, which is Cedra Smith's microelectronic circuits. And this one, we only need 2 chapters from the book, from this book, so you don't need to purchase this either. And actually, I will upload those 2 chapters, the PDF, to the Canvas, so you can take a look. So we don't need too much materials from the second book. So with that, the most important resources for you is the lecture slides under files in the Canvas system, and especially the marked version. After we have done our discussions in class, then I will upload the marked version to the Canvas, and that is your most useful resource for this course. So any questions? All right, so let's have some discussions on the course objectives. And here, as the title suggests, physical foundations. So in this course, we are going to deal with physical aspects of computation. And the perspective of this course is as follows. First, we know that the digital information is represented by 0 and 1s in the digital fashion. But actually, in the actual hardware, those information are carried by electron or holes. We are going to discuss that later, in the form of voltage or current. So essentially, you are using voltage or current to do the computation, and you interpret that as digital 0 and 1. And the voltage or current, for example, the current is in the form of electron flow. And we are going to discuss that in more details, how would the electrons flow in a device. And here you see a terminology, holes. We are going to have more discussions later. But simply speaking, the holes are the opposite of electrons. For example, electron carries the negative charges, then you can think the holes carry the positive charges. So it's just opposite to the electron. And we need to understand that information processing is done by electronic switches to allow or block the flow of electron or holes. And essentially, we call this electronic switch as transistor. So this is the fundamental building block for all the digital system. For example, your microprocessor is made of billions of transistors. A single transistor is the smallest unit that you control the 0 and 1 in the form of the electron flow or hole flow. So we are going to have more discussions in this course about the transistor. And also, we need to understand the information in the system is carried to different parts of the chip and the outside world through the metal wires. And we call those metal wires as interconnects. So those metal wires is going to communicate different part of the chip or communicate this chip with outside world. So this is through the interconnect, and this is done by the metal wire. We are going to have some discussions about the interconnect in this course. And lastly, the information are stored by electrons trapped in some metal or dielectric layer in certain devices. Essentially, here we are talking about memory devices. If you think about your information system, you need to process your information, and also you need to store your information in some devices. For example, your SSD, solid state drive, right? You store the information in the drive. So we're going to discuss the fundamental building block, how to store the data in the computer system. So if you think about the three pillars of a computer system, we have already mentioned that in the previous slide, but here is just some cartoon for you to better view the system. So there are three components. So first one is for computation. So you do your computation, like your, let's say, like adder, you add two numbers. So then this is done by the logic, digital logic. You can write down the equations for the full adder, and then you need to use logic to do the computation. Essentially, you can build any system using just, for example, NAND gates or LOR gates, right? So then those are done by the logic. And logic is eventually realized by the transistor we talked about earlier, which is the fundamental building block of the logic system. It's called a transistor. It's a single device. And then this is for the computation. But after you do your computation, you need to save your output of your computation into some memory. This is for data storage. So we need the memory for the system. So the first one is logic. This is to do the computation. And then we need the memory to store the data. And we're going to discuss the memory technology in this course as well. So there are different memory technologies in the computer system to store the data. If you look at the specs of your, for example, smartphone, you will find out the, for example, the RAM, right? You have 4 GB RAM to save the data. And also you may have like a 64 GB SSD to save the data. So what's the difference there? Any idea? Yes?
RAM is persistent, so it's only like temporary storage.
Mm-hmm.
SSD is persistent, so it lasts for longer.
Yes, that's correct. So RAM is, in our words, we call it volatile memory, and in your word is non-persistent, but basically the same thing. So after you remove the power supply, then your data is gone. So then it's volatile, and this is RAM. And then for the SSD, solid state drive, it's non-volatile memory. That means after you remove the power supply, the data is still there. So this is for longer time data storage. So this is the memory technologies for computer system. And we are going to discuss the device technologies for those RAM or SSD in this course as well. And then we have the logic and the memory. And then we still need the interconnect to communicate different parts of the system. For example, if the logic wants to talk to the memory, then the signal needs to go through the interconnect between logic and memory. And typically, it's done by the metal wires on the chip. Then this is called the interconnect, and this is for the communication. So if you think about the system, you can have those three components. And all those three components are made of actual hardware. And we are going to discuss the hardware in this course. All right. So if you look at the computing, and this is the first stack of the computing from very top level application. You have different kinds of tasks for computing, right? Here are the applications by those programs. So I will not name all of them. You know those notebooks, look very familiar to you. But if you run those applications through the software, the program needs to be compiled to the hardware language, like your assembly language, and then it will be translated to the instructions and to manipulate the 0 and 1s, essentially. And then this 0 and 1s will run on certain architecture of your, for example, microprocessor. And the microprocessor are made of different circuits, maybe multipliers or adders. So then those circuits essentially are made of devices here. So then these devices, as we discussed, for the logic, the building block is the transistor. So those circuits are made of maybe thousands or tens of thousands devices. And a single device is called transistor. And then the transistor here is actually made of materials of mostly silicon. Right? We talk about silicon technology these days because the material we used to build that transistor is mostly silicon. So we are going to discuss the, let's say, in this course. Okay, this is the full stack of the computing. If you look at your computer engineering programs, then basically you are going to learn all the aspects in this stack. But in the 3030, okay, we are going to discuss mostly the bottom part of this stack, which deal with the materials and devices, and maybe a little bit circuits, devices, materials. So any questions here?